On today's webinar, we'll be presenting some solutions for power applications. My name is Odair Rodriguez from Ion Associates, and I will be co-presenting with my colleagues Marvin Govindan and Raul Dominguez. Every application needs some kind of form of power, be it AC power from the mains or battery power from a rechargeable source. Today, we're going to focus on solutions for an end model or for you to design your own system. This will be the main content that we'll be requiring reviewing today. Next page. As we can see, we'll look at the basic or AC and DC voltages. We'll also be covering some options available in terms of off-the-shelf solutions or building discrete solutions. We will also look at distributed power systems or point of load. We will look at specific products from some of our partners, such as MaxLinear, GaN Systems, Littelfuse, and battery backup solutions. There are also a range of complementary solutions that we should not forget about, such as connector, energy monitoring, and control relay. So, when we talk about power products, we don't only refer to AC to DC or DC to DC solutions. Electronic power delivery systems are also found in motor control, power audio systems, or designs for communication devices such as data centers or 5G towers. But before reviewing specific products, let us review some of the basics of power. Now, let's move over to my colleague Marvin Govindan, who will talk about this part. Thank you.
Hi, everyone. Thank you, Odair. So we're going to just have a technical recap on some of the things we've seen in the past on the basics of power. So in this section, we're just going to have a recap on the basic aspects. So here we're going to talk about AC and DC voltages. We're going to look at modules or discrete solutions, touch on some providers like ABB that can supply some of these products. We'll look at some applications. We'll also look at power supplies, which are dedicated already built power supplies for AC to DC. There are also some DC to DC options there we can have a look at, bricks, point of loads. And we're going to talk a bit about how we can measure and monitor energy. Sometimes it's good to monitor the energy being consumed. Sometimes it's better to calculate. So we'll touch on some of these subjects just as a recap before we see more product detail. So just a quick reminder, what we get from our mains, from the sockets in our homes and in businesses, we get sinusoidal AC voltage, which can be at 50 or 60 hertz, depending where you are in the world. So in the US, that could be 110 volts. In Europe, that could be up to 220, 230 volts. Latin America, it could be something like 127 volts. Then we have special cases where on the post in a lighting system, we might find 277 volts. And we also may have monophasic systems or three-phase systems. So the installation as well might give us access to live wires, a different number of phases and a neutral or just pure phases. And we have to tap off those lines. So when we take those voltages, we normally have to rectify them for a lot of applications. So we'll rectify those and we'll get a DC voltage out of that. So that could be, 90 volts rectifies to 127. It could be 240 rectifying to 340. So all our components that will go into our circuits have to tolerate that voltage and voltage spikes in DC. So that could increase maybe 3 to 5 times on those lines. So depending on our circuitry, we need to protect those with the correct components. And also we have that changes as you get to higher voltages and we start tapping off 2 phases and getting really high voltages. we have to take into account if our input circuitry will withstand those voltage spikes and variations. A lot of our apparatus, as you will know, use universal voltage supplies that could be anywhere between 85 to 264 volts AC. And we tend to see those on the adapters for our computers. So also in power, just to recap on what we've seen in the past, when we have a circuit, we use these basic formulas to check our components. So we use the I²R formula or the current times voltage formula to check our components, make sure the right power rating. We look at how power is transferring through from one circuit to the other, if it's efficient or if we're maximizing the power transfer. On the power side, coming from the line, we have delta and star configurations, monophase and three-phase systems. Many times a project may require, they might just specify a voltage coming in from the line. And what we find is when we go to installations, we don't have the power lines we expected. Maybe we're expecting a phase and a neutral, and instead we have two phases, very high voltage, and we need to step down or do something special there to make sure we're not inheriting all the noise that's coming from that line. So, you know, depending where you are in the world, you might see a star or delta configuration, and we have more information on that if you need. For monitoring, we come across a lot of different ways of measuring energy, and that could be using Rogowski coils, like windings, current transformers, shunt resistors, Hall effect sensors. There's many ways to monitor these, the power being consumed in an installation or on a circuit. Basic power relationships. I think the most basic you can get is how is power defined? It's the work done over a certain time. So power traditionally is measured in watts. If we go dig deeper, it's joules per second. And so we're looking at the work done or energy used in joules over a certain specific time, which is normally measured in seconds. So we can, looking at these formulas, we could estimate the energy of say 100-watt bulb that's on for 8 hours. We look at the time in seconds. We see what the power is in joules per second, and we can calculate the energy that we're actually using in kilojoules. On circuit boards, this is very basic. We select components. Sometimes we overlook those things, and we misdimension part of the circuit, and we get lots of local heating. I've come across this a lot, and sometimes we just slap on a resistor somewhere, and it seems to be working fine for a while, and it's actually working under its limit. It's overheating, it's burning. So yes, we have to sort of check all the power ratings of our components on the circuits, and we can use these formulas to do that. I²R and V²/R. What other things do we come across commonly now? So years ago, when there was only light bulbs that we had to worry about, a light bulb, an incandescent bulb, has a power factor of 1. I mean, it just it doesn't have any issue in terms of changing the phase of voltage with relation to current. But as we've used power supplies now, which like switch mode power supplies, we use motors, we have inductive loads. We can shift this current waveform in relation to the voltage. So if you put them into antiphase, we're getting a real power delivery of 0. And what we try to do is correct for that phase shift. We want those two things in as much in phase as possible. And for many standards, we need to have a good power factor rating where they're almost in phase, above 90%, we'd say. So for certain circuits, it could be luminaires, it could be IoT devices. We have switch mode power supplies, and one of the stages in there, we're going to put a power factor, active power factor circuit. So we literally measure the voltages of current coming in and the current of that's being the current waveform and the voltage waveform, and we adjust the time, the duty cycle to put those two in phase again. So and that's almost a standard requirement for lots of IoT devices, especially if they're connected to the mains, luminaires, things which are connected to the mains line, but they have a switch mode power supply. So On the right-hand side, you can see a typical topology that you may come across. And at the bottom there, you may see the vector representation of apparent power, which measures in kilovolts, amps. And you might have real power there, which is in kilowatts, and how they're related. The angle there is the power factor angle, which is cos phi, you can see there. And that's one way you see it represented on your devices. Also, obviously, for smaller devices, we don't want to put an active PFC. It's too much cost. So you put in basically a low pass filter, and that does some of the job for you. So that's a passive PFC circuit. And we tend to add those in for smaller circuitry, low power, just circuits which are running at a few watts. So we have that option as well. Just to mention once again, what are the effective inductances and capacitors in AC circuits? We have an inductive circuit there. The current responds after the voltage. It lags the voltage. For purely capacitive supply, that would be the other way around. The current would lead the voltage. Okay, so that's what the effect of these components, these types of circuits, inductive and capacitive, have on the current and voltage waveform. That's why we need to correct for these. Okay, so what does that have? What happens with power factor? Well, if we have simple way of thinking of it, a low power factor means we're more inefficient. Our circuits are more inefficient. The current is inversely proportional to cos phi, that angle we talked about. And a low power factor, as it says, there will result in a higher load current and higher losses. So we do try to keep that as high as possible. And depending on your application, there may be a requirement to be above a certain level. So depending on how your system is being measured and what you're using, it's something we sometimes have to look at. Also, we have power systems, which are just DC power. They're running off batteries or battery bank. Or it could be an IoT device. We could be measuring the power consumption, or we could be estimating the power consumption. So taking a simple example, we could take a LED luminaire. We could measure the voltage going in, the current being consumed at various parts of the circuit. After rectification, we could look at the rectified voltage. Then we go through our power factor corrector circuit, and we go into our driver stage, and we start to see the DC performance of the circuit. So we'll get a certain number of watts out of it. So because we know what we're generating, we're taking from the main side in terms of watts, and we know what we're calculating on the output side in watts. So we can see how much we're actually losing in terms of efficiency. So by knowing our circuit well, we can analyze that and say, okay, I'm going to reduce my losses. If I have certain components, I'm going to reduce as much as I can the forward voltages, and you can start to analyze the power losses in your circuit to become more efficient. So just dealing with the multimeter, take a multimeter, do some basic measurements. Then from there, we can say, okay, we can look at our magnetics provider. Okay, do I have losses? Am I having losses in the core, in the iron, in the ferrite material, hysteresis loss? Are there eddy currents? There are formulas for all of these, and this is where we can start to say, okay, I need to be more efficient. Maybe I need to change some materials or some parameters in my construction to reduce my losses. And also in my circuit, well, I could have diodes there, but I could say, well, I'll take out that silicon diode, I'll put a Schottky diode there, I'll have less forward voltage, and that will reduce that power consumption and that heat dissipation on that device. So we can start looking at the voltages that we can reduce on those parts of the circuits and increase the efficiency. Especially when the things are running hot, the voltages tend to increase, there's more heat dissipation, we start to get more losses at higher temperature. So we can start looking at how to reduce those power losses. And also, we have to consider sometimes, if we're going to monitor a device, we can add in circuitry, we can add in current sensors, an IC that measures the energy being consumed. But then, is it overkill? I mean, are we should we be measuring it? Because that's gonna, if we're using if it's a battery powered application, we're gonna run down that battery quicker because we have more circuitry. So what we can do is, if it's a device that has a certain behavior at certain times, it has sleep modes, it wakes up, when certain functions are on, certain parts of the circuit are on, we can estimate the current. We can use like shown here, a pico ammeter. We can measure how much consumption we're having on these parts of the circuit, and we can characterize it. And our system can be intelligent to know that once these functions are on, it times how long they're on for, and it estimates the power consumption. And that could be better in terms of battery life. It means that you're sort of estimating how much energy is being used, how much you're running down your battery, and you're saving on the circuitry, which is going to drain the battery quicker. So that way you can extend the lifetime by taking into account sleep modes, wake up modes, and brightness. So you've said IoT device brightness of displays. You can sort of estimate in a data logging fashion how much your device is consuming. So you get the work on the front end. You know how your device works, and you sort of do a data logging function to do the energy monitoring. So that's an alternative way of monitoring your energy. So now I'll move to the part where I talk a bit about one of our providers, ABB, who have embedded solutions. They have point of load, bricks, AC/DC power supplies, and distributed power system solutions. So what we see here, point of load, we're going to see some bricks, isolated solutions, non-isolated, and we're going to look at maybe some things that are useful to us when we're developing our product, okay? And we'll touch on rack power and some possibly applications. So what is a power brick? Think of a brick as a rectangular object which you build your house with. But yeah, so here we have a rectangular object. Sometimes it literally looks like a metal brick. It has a casing on it, which is nice and metallic and has a label on there. But the form factor is basically, it's a standard size and has a standard footprint. What is the advantage of having a brick? They're available from many manufacturers. They conform to a standard made by DOSA. I can think of that as an agency that have standardized how these bricks should work, what types of voltages they should have, what the thermal performance is, and many characteristics, and they're all certified. So if you have an application, you may have 2 or 3 providers on the same design. So you can buy from the same product from 2-3 manufacturers, and it will work the same. Okay, and there are certain customizable characteristics like trimming the voltage and current, and on each of these bricks as well. Okay, so DOSA, there's the link. I put the link here on the screen, but you can have a look at this. What the specifications are. But here you have 6 standard brick sizes. You can see the image on the right hand side where you have full bricks, half bricks, quarter bricks, 8 bricks, 16 bricks, and well, smaller 1/32 size bricks, 32nd brick. So the power density is important. It means you can obviously the more power you can pack into a smaller area, it may be more attractive for application. If it's a card for a telecom rack, where you say board space and the whole size of the rack can reduce considerably, that tends to mean also that the heat generated in that area will be higher. So your thermal solution has to be better. And hopefully that means that also the technology has improved so much, it's not generating as much heat as say 5 years ago. But yes, you can save board space, and that can be attractive. So what does that mean? What do these bricks and these point of loads mean to us? Well, they're drop-in power supply units. They're certified, they're tested, they're easy to integrate. So if you have, say, 15 different cards in a rack which perform different functions, well, you can have maybe 2 boards there where you are supplying power to the whole rack in a redundant system. They could have, so you have an AC/DC coming in somewhere in your system. So you're getting 48 volts out to the rack, you could say. And from there, on those two boards, you have you distribute the power into the power lines you need on the board, which could be 12 volts, minus 12 volts. You're thinking of like op amps, if you have op amp circuitry. You could have 24 volts or 5 volts, 3.3 volts, and you distribute these out on lines on the backplane. So some of the boards can be almost dummy boards. They just get power straight from the connector. And that way you centralize the power in that tributary. And so it's very good, it's certified, and you can maximize on volume. If you just drop in bricks onto your designs and everyone who's working on a card uses the same bricks and uses the same power supplies, well, you've sort of normalized the design. The volumes are better. You're buying more of one part from a supplier, so you can negotiate better costs, and the performance, be it good, will be sort of replicated across the board, which means your calculations for fit rate, for your mean time before failure, all of that can be normalized and standardized. So there's a big benefit to dropping in a brick onto a design. But yes, also we have to look at losses. And so when you have a backplane, you design a backplane normally, and sometimes you'll put 12 volts in on one end and you get to the other end of the rack. Lots of things are connected on there, and you'll see maybe a power drop. Maybe you're losing half a volt on that line. So a lot of these bricks, a lot of these products have a trim pin, and you can either do it via a programming system that's a PM bus that the device may have, or you just adjust a resistor to compensate for any losses you may have on the backplane. Again, the application everything is application dependent. There are isolated versions of bricks and non-isolated versions, and that depends on the application and the safety and standards you require for your application. Reliability, for all these products that you'll see, there's reliability data, and that helps and that's the difference between maybe something which you develop yourself. These things are tested all the time, and they have the reliability data and the fit rate data is something which is sort of telling you this is a product where you can offer a good guarantee your product will not fail unexpectedly. So these things can be calculated. So yeah, this is an example here. You can see an image of a rack, and you can have distributed voltages in the backplane. You have PSU replication over the different boards. You have cost savings in there in terms of volume because you're using the same types of bricks and point of loads. And obviously, depending on what components you have in each board, you may see various voltage. It could be 1.8 volts to 3.3 volts for your MCUs. Op amps that running at 5 volts plus or minus 12 volts. You may have IGBTs, you may have other things going on there. So you can sort of select the bricks you need and add those in onto one board and distribute it across the rack. On this slide, we can see different types of products that we have. We have products that supply power over 150 watt modules in certain small sizes, you can say. Quarter brick and 8th brick. As I mentioned, usually you have maybe 48 volts coming into certain racks, and so 36 volts to 75 volts falls well within that range. We have low power, it can be 15 watts to 120 watts in certain sizes. We have 15 to 228 watt formats, 100 watts. We have the ATCA PIM modules, which are telecom compliant modules, like a standard design. If you have telecom boards there, this might be a dual redundant design which you want to consider. This is compatible with other manufacturers as well. And sometimes you might need an extra filter module to improve your EMI. So we have those as well to concatenate with the solution you're looking at. These are the isolated DC versions. This is a table, a summary table of what you can see. What we really need is just to know what your application is, what power you need, voltage, your input, your voltage input, the current you're looking for, and the output current and voltage that you need. And with that, we can sort of define which family falls into your product that you need. Similarly, if isolation isn't critical, if this thing is not so accessible and you don't need full isolation between the primary and secondary sides, then you may have We can look at non-isolated solutions as well. So we have lots of these small power supplies, these bricks, where we can we might have to step down or step up or step down in voltage. Sometimes we might need a digital analog interface. We have these variations as well to be able to talk to the device, maybe do some configuration. And we have different power ratings as well. So it's, again, looking at this next slide here, we just need to discover what is the input voltage you require to your system. If it's 12 volts, if it's 16 volts, or what it could be, the current you need out of this device, and the power rating, and what voltage you need. So, and with that, we can define the best product. Just more of a closer view of this is one product we have here, 20 amps out, efficiency 95%. It's a constant voltage device. We have other features: over current protection, over voltage protection, under voltage lockout, and we have the control via something called the PM bus, which allows voltage adjustment. Okay, here you can see sort of what the footprint is of the device, and you can obviously compare that to any other device you're looking at. And this is the ACTA PIM module, which is 48 volts in. It's dual redundant. It's for these telecom boards. This is sort of a standard product. It's hot swap capable. It has an integrated EMI filter and I2C interface. Again, efficiency 98%. So as you see with these modules, if you need to drop them into a design, we can supply all the documentation for that. Here is the EMC module, which you might want to concatenate here, as you see in the image, a filter module. If you need to comply with certain EMI conducted emissions testings, and you need to see what this performance is, that's something we can supply to help you pass those standards. There's reference circuitry on the data sheets which can help you to implement that. And if you need more information on that, we can send that to you as well. This is a low power version, a Stingray it's called, 10 amp output. You could have 48 volts coming into this, constant voltage. Again, we have the features that we saw, PM bus, over current, over voltage protection. And for all these designs you just saw, if you need the step files, those are available as well upon request. So you could just say, I have this design, I need to drop it onto my board, I need to make sure it all fits well together. You can ask us for that, and we can get those. And that saves you a lot of time as well. Now moving on to this section, it's the AC/DC power. So we also, sometimes you want something which is ready-made. There's a whole selection. There's a COP series. These are constant voltage power supplies, not really for LED luminaires, but for systems which need to maintain constant voltage. We have 12 volts, 24 volts, 54 volts. We have lots of power, a high power range here. These are good supplies with high efficiencies. They can be open frame or closed frame. And more importantly, you may see a lot of things like this commercially in city centers, which look very, very similar. But what you don't see is this MTBF. You won't see the high reliability performance, because these things are tested to have a very high reliability. You may see a lot of other, let's say, Asian product, which looks exactly the same, but they won't have the same level of reliability. So if you need high reliability, a long life for your application, it's very good to look at these specs, this part of the spec. Rack power, if you have data centers, telecoms, telcos, they're going to need some high kilowatt power supplies, and we need to distribute power across that rack. And so we have lots of different solutions which will accept AC and will give out maybe 48 volts DC that you need, but in terms of kilowatts, and that's distributed across the rack. A lot of the times you want these things to be dual redundant. So if we need to pull one out for whatever reason, we can hot swap it and plug another one back in. So we have these things available as well. We can see a version here, the Resilient 3000, high power factor, load harmonic distortion, high efficiency. And this is something we can look at for redundant systems. Okay, so this would be on the AC side, maybe then putting out 48 volts. Because to some systems, it is good to centralize the power in a way where, you know, it's one point of failure and we can easily replace or make it redundant, so it's highly reliable. So talking about distributed power, let's look at an example. Greenhouses, for example, there's a lot of horticulture products happening right now. It's a boom industry. So you might be monitoring plant growth and artificially controlling the environment in a greenhouse. So we're looking at Wi-Fi, Bluetooth, dimming, certain wavelengths of light. We will have alarms and sensors inside this facility. So the first option could be to have lots and lots of fixtures here with IoT modules in there doing the sensing, doing the monitoring. And these could run off AC. We could distribute AC around the system, just like in the home or in the industry. So each, say, troffer would need one power supply, and we have to do the AC-DC conversion. We need power factor correction and everything. The other option is to maybe we'll put in a rack somewhere in the system, and we'll have a maybe 2-3 kilowatt power supplies, and we'll distribute 48 volts around this greenhouse, and we'll run off voltages, DC voltages, and then that way we'll save on installation of power supplies in every single light fixture in these vertical farms or these greenhouses that we have. So just here we could just say, yeah, we could have 127 volts input, we'd have DC conversion, we'll have a constant current stage for the, say, LEDs, and for the IoT part, we need constant voltage stages. So there's a lot of blocks there. Or we could get rid of the AC stage and just have the convert from that 48 volts, we'll have 12 volts, 5 volts, and 3.3 volts coming out distributed through the backplane, and just have maybe the boost stage for the LEDs, and we've got rid of a few stages there. So that's another interesting way that we've seen implemented in greenhouses. So we don't always use AC to DC, we can use DC DCs and a rack solution. So so basically we're distributing the power. The advantages, we're distributing the power with point of loads to a certain quantity of fixtures. It's not conversion inside every single fixture. We're managing the power centrally. It's a centralized power distribution system, so we can monitor what's going on at one point. We've removed some lots of individual stages of PFC correction, and we've increased the efficiency of each fixture as well. So doing this, we've increased the reliability of our whole installation. It's more robust. And just to build on that, depending on the application, depending on the power that you're generating, you generate heat. So we have options for dissipating that heat. We have thermoclad. So here, if you have a circuit that's getting hot, you might want to distribute that heat away. So we have aluminum substrates, copper substrates. We can assemble the circuitry on the metal board instead of FR4. We spread the heat away, and additionally, we can mount that on an aluminum heatsink. So this is another, it's a material we can use to help dissipate the power. So even for low power applications, but up to high power applications, we have this material which we can use to help extract heat from our circuits and increase that reliability. And that's all from me. I'm going to pass over to my colleague on discrete design.
Thank you, Marvin. So during this session, we've been covering, or we have covered some solutions for end models or plug and play solutions. We also, on the last slide, we review the products, some of the initial products that we could use for a discrete solution. That is the part of this, or that is what we are going to talk about in this section. We already saw the AC to DC models, the plug and play, but what do we need to design our own system? Maybe because of some specific requirements, or even because we need to have some proprietary solution. not only for the AC to DC solutions or DC to DC solutions, but also for some other products that we might want to use. We can, as we already saw on the first slides, we might need to control a motor or design a system, a power system for wireless, high power wireless products, for communication towers, for motor control. And so the idea for this section is to talk about some of the products, some of the suppliers of the partners that can help you to design your own product. For discrete technologies, we might start to talk about maybe IGBTs or MOSFETs, where they can be. When we talk about MOSFET, for example, we've seen in the market traditional silicon technology, but in the newer days, we will see silicon carbide or GaN technology. Silicon carbide and GaN technology will help us on improving the efficiency of our product as a result, or switching that higher frequency and reduce thermal dependency. Not only the component is the FET is the one that will be affected. With this higher frequency working at higher frequency, we can reduce the size of the inductors, the transformers, or even heat sinks. So the final result, the final product, the product that we can achieve with these technologies will be smaller. Okay. Talking about power solutions or solutions provided by our partners, we can look at Littelfuse, for example. Littelfuse is a partner that can help you with products for a design or a discrete design solution. They can help us with silicon or silicon carbide technology. As we can see, Littelfuse has high power diodes, MOSFETs, IGBTs, or for even higher products, IGBT or thyristor modules. As I said before, we can use silicon technology or silicon carbide. When we talk about IGBT or MOSFETs, we need to consider the gate drivers for these technologies. So for these technologies, Littelfuse can help us with some recommended products, depending, of course, of the requirements of the application. With silicon carbide, the portfolio for silicon carbide is really big. We have products for diodes and MOSFETs in surface mount or through-hole package. The RDS(on) for the MOSFETs, for example, can range from 180 milliohms down to 25 milliohms, and their technology keeps improving. So we will see in the better products, for example, with lower RDS(on). On the part of the diodes, we can see proposals that can go between 5 amps up to 120 amps. And of course, these all different values will depend, of course, of the families. We'll find families for 100 and 1200 or 1700 reverse voltage. That is, for example, solutions for silicon or silicon carbide. We're seeing in the market some other technologies, GaN technology, which, like I said before, will help us to improving the efficiency and reducing the size of the board or the final board. On this part, for example, for this purpose, our partner GaN Systems has a wide portfolio or GaN FETs, and of course, with them, we will find many reference designs. Next slide, please. We will find many reference designs. They can go maybe for the basic, we want to call it like that in talking about power systems, like chargers or adapters. Also for power supplies, a discrete power supply, we can find solutions for 300 watts, 3 kilowatts, audio amplifiers, or even wireless products, 50 watts, 100 watts, 300 watts, or data centers, RF and 5G technologies. As you can see, we have for the FETs, we can help you with different technologies, and also we can help you on solutions for DC power systems, or let's say low power solutions. On this part, with our partner MaxLinear, we can find modules, we can find solutions, DC to DC modules or point of load up to 20 amps, or DC to DC converter, or even PMICs for the high performance processor, DSP, or maybe FPGAs. Next. Another different view of the solution that we can offer with MaxLinear. As I told you before, we have the PMICs, we have the modules, which have the inductors and the discrete components inside the package, or a more discrete solution, the DC to DC converters. And for, well, complementary solution for this, the LDOs for low power systems. Also, well, on every, talking about DC to DC solutions, modules or controller, it's important to consider capacitors. With Taiyo then we can support you with an extensive portfolio of MLCCs in different series, depending on the requirements. Multi-layer ceramic capacitors can come in size from 0201, 0402, or up to 1210, for example. And of course, the type can vary between X7R, X5R, NPO, depending on the value and of course the application. The values are available from magnitudes from picofarads up to microfarads. All of these components, we can help you with the selection of every of these parts. And continue on the a discrete solution. We might need, for this kind of solution, bigger current, high power, we might want to consider a solution or component that can help us into measuring the current, for example, of the components or the entire system. In this part is when called Rogowski coils or current transformers can help us into this measurement. With Pulse, with one of our partners, Pulse, we can help you with current sense magnetics. We will basically have maybe two different options. Above, we can see solutions in SMD or two-hole package with the capability of measuring from 4 amps up to 100 amps. Or if we want to a solution that can be assembled directly into the wire, we have on the downside of this slide, the white side window family. They have the capability to measure up to 4 amps or even 1 kilo amp with the accuracy of 0.2%. So they're really good. Moving forward and complementing the solution for the not only for the current but also for the energy measurement solutions. With Cirrus Logic, we have ICs that will help us to measure active, reactive, and apparent power, or even instantaneous voltage, current, and power. We have many reference designs that are perfect match, for example, for some of the products with Pulse. So we can help you with this combo solution. That would be all, most of the solution. For example, talking about the discrete components. Now we'll talk about the battery solutions with Raul Dominguez.
Thank you. Now with this Industry 4.0 and the IoT, we are seeing that many devices are going off the grid, meaning they need batteries. For this, we need to consider several things. For example, here we are seeing a case of a 120 amp hour battery with a discharge rate of 15 amps. And we can see in the graph that if we draw more amps from the battery, the total capacity is diminished. So we need to consider this when we are selecting the battery according to our own device that needs certain current, certain peaks, and to know how much it needs to be alive. Next, please. Also, one of the more known technologies are lithium right now. With lithium and almost all the batteries, we need to consider also the temperature. So the rating and the capacity is almost always at 20 degrees. 25 to 27 is the optimal condition for many devices. Below that, the capacity is diminished. There are some batteries that can work and withstand charging and discharging at minus 20 degrees C, or even being discharged at minus 30 or minus 40. But those are special batteries that we can find. But we need to know what is the usage, what is the temperature expected, to consider those in our calculations. Next, please. Also, normally we see all the batteries that are rated in milliamp hours, the smaller ones, and ampere hours, the bigger ones. What is this? 1 milliamp hour is 1,000th of an amp hour. So here's how we calculate how long it will work for our device. For example, a battery of 1,000 milliamp hours. Our operating current, the normal, is 2.5 milliamps. So we divide 1,000 between 2.5, and we will know how many hours the device will work with that battery. Remember, we find the rating for several reasons, like temperature, aging, charging, discharge cycles. So all of this we need to consider to know what we can offer to the end user. Next, please. So, as we're seeing, lithium ion is the best known storage technology right now. It's the most common because right now we couldn't be having so many disconnected devices from the grid if we couldn't recharge them. If we use only prior are the batteries that can you buy on the store, and you can use only one time. Imagine the quantity of batteries we would be needing. For example, in the cell phone, we need to charge it sometimes twice a day if we use it several heavy usage, or once each 3 days. Imagine if we couldn't recharge it. So that's where lithium ion is entering, because this withstands good cycles and good capacity. For the applications, we can see lots of them: mobility, e-bikes, scooters. We see vehicles that are hybrid or electrical vehicles now, the mass transportation buses, heavy machinery, handhelds, drones, power banks, white goods. So everything is to move to this battery application. Next, please. So with TWS, we have several kinds of batteries we can offer, depending on your needs. Here, I will show some examples. It's not that we only do those, but it's to show what we can do. For example, these emergency calls. This kind of battery needs to survive a crash and needs to work in extreme environments because it's for emergencies. So it can withstand discharging from minus 40 to 85 degrees C. So 1 second, 2 seconds, or if the battery is failing, will mean that life is lost. Next, please. Now, with the industrial handhelds, they are expected to withstand extreme environmental conditions, being lightweight and have long times on the operating stage, because you don't want to be having a handheld in the industry and have to recharge it every 2 hours. You want to work it at least a day, heavy work, and withstand it. So we are working with several companies doing handhelds and these kind of devices that can withstand environmental and also withstand the vibration. That is very important. Next, please. Vacuum cleaners. So now we are going to see more and more of this kind of devices, robot ones or handheld ones. We are expecting the battery to have a lot of power to power up a good motor, because if you don't have a good motor in there, the device won't perform nicely, and then your customer will be disappointed. So we have several options available for you. We are right now helping upright vacuum cleaners, stick vacuum cleaners, handheld, robotic ones. So we have experience in this. Next, please. For material handling, you have seen this kind of forklifts. They are transitioning from gas to battery because it's less risk having battery compared to a gas. It's easier to charge because at the end of the day, you just plug it to the wall and it will charge. And in the other hand, with the gas ones, you need to change the cylinder or take the forklift to a special area to do this service. So this needs a lot of power to move all the machinery, and we have the solutions for you. Next. With the PDA models, you can see that you need a lot of power. You need to be flexible in the pack design. You need them to be not that expensive, because these big packs goes in vehicles. Normally, you need several cells of these to move the equipment. And cost and reliability is a very important part of it. Right now, we have batteries in electric passenger cars, in electric buses, in light electric vehicles, for the golf carts, and also with electric excavators. Next, please. Here is a glimpse of what we offer. This is one cell that is released. It's just like a AA battery, little bigger. With this, we do bigger battery packs, but we can use any cell available in the market. If you need certain chemistry, we can use it, and you will have it. For example, in this, we have 2600 milliamp hour. It can withstand a discharge current of 15 amps, so it's very high. The operating temperature, you can see for charging, goes to -20, so it will be lower charge, slower, but it can do it. And on the operating temperature, you can see that it's from -40 to 85. Remember that temperature affects the capacity. So at -40, we won't see the 2600 milliamp hour. We will see less, but you can do it. You will have a device working. Right now, it's very difficult to find this kind of batteries, so we can have them. Next, please. Here's another example. Here's for a big battery pack, 135 amp hour, 33.3 volts. So it can withstand 135 amps. It's a lot of juice, a lot of power. We can withstand peaks of discharge of 400 amps. So this is the kind of batteries we use, for example, for the electrical excavators that would need this kind of peaks and high amperage. So we can help you. We have capabilities to do the design of the batteries, to do the external cases, to include the battery management modules, the BMS. Depending on your need, we will help you and we can do a design for you with TWS. Now, let's go back with Ariel. Thank you.
Thank you, Raul. So, well, this is the last part of the last section of this presentation. We wanted also to talk about complementary solution that might apply to any of your designs. For example, next please, with Amphenol, you know, many or most of the designs, most of the products require something that can help us to make some connection or interconnection between devices or between boards. For these purposes, with Amphenol ICC, we can help you with power connectors. Depending on the family, we have the capability or the support maybe up to 1 kiloamp or 600 amps. So as you can see, we can help you with some recommended products, whether they are pre-assembled, SMD or to-whole package. Okay. All the applications may apply to all the products that we talked before, telecom, networking, even EV charging, robotics, or UPS products. Next. And well, this second continuation of another slide of the products that we can offer. So we can help you on doing the selection. We can help you on identifying the products that match or better fit to your needs. You just send us an email, contact us, and we will be available to help you. Some other products that we might consider is the relays or contactors with the other partner, with what or of our partners. Set relays, we can help you with not only industrial or high power relays, also EV charger relays or contactors and circuit breakers. Okay, so